Here's a problem most people never think about, because most people never need to. A power plant needs electricity to start. Pumps need power. Fans need power. Control rooms, safety systems, the machinery that gets a turbine spinning in the first place. All of it runs on electricity from the grid. So what happens when the entire grid goes dark? Every plant that could turn back on needs power it doesn't have. It's not a supply problem. It's not a demand problem. It's a chicken and egg problem at the scale of an entire country. Right now, 10 million people in Cuba are living this exact question. Their grid has collapsed for the 4th time this year. And restarting it from nothing is a genuinely different kind of engineering problem than keeping it running. Here's how it actually works. Start with what a power plant actually needs just to turn on. A coal plant needs pumps to move water, fans to force air through the boiler, conveyor systems to feed fuel in, and a control system to manage all of it safely. A gas plant needs ignition systems, cooling, and compressors. A nuclear plant needs all of that plus multiple layers of safety-critical backup power, because getting it wrong isn't an option. None of that runs for free. Every one of those systems is, itself, a customer of the electric grid. In normal operation, a plant draws a small slice of its own output to run its auxiliaries, pumps, fans, controls, and sends the rest out to everyone else. That works fine when the grid is already up. It falls apart completely when the grid is down. A plant that needs grid power to start cannot start the grid. If every plant on the system works this way, you have a few hundred machines, each one waiting for the others to go first. This is why a total blackout isn't just no electricity. It's a system that has lost the ability to bootstrap itself back on. There's a way out of this, and it comes down to a small number of power plants that don't have the same problem. Hydroelectric plants are the classic example. Open the intake gates, and flowing water spins the turbine directly. No pumps, no ignition sequence, no combustion to manage. The generator can be brought online with only a small amount of external power, sometimes none at all, just to control the gates and excitation system. The other option is a small combustion turbine or diesel generator, purpose-built to start on its own battery or a local backup supply, without needing anything from the grid. These are called Blackstart resources, and they're not optional or improvised. In North America, NERC, the organization that writes and enforces grid reliability rules, has a specific standard for this. It's called EOP 005, System Restoration from Blackstart Resources. It requires every transmission operator to designate specific Blackstart units, maintain a written restoration plan, train the crews who will execute it, and actually run drills. Most of those crews have trained for this exact scenario for years. Almost none of them have had to use it against a real, full-scale collapse. So a Blackstart unit comes online. Now what? It doesn't just dump power onto the grid. It energizes one specific, pre-planned segment of transmission line. Engineers call this a cranking path that connects it to the next plant in the restoration plan. That next plant doesn't need much. It just needs enough power to spin up its own pumps and fans and controls, the same auxiliary systems that were the whole problem earlier. Once that plant is running, it can add its own generation to the mix, and the two of them together can now energize a cranking path to a third plant, and a fourth. Each step creates what operators call an island, a small, self-contained patch of the grid that's live, stable, and completely disconnected from every other island still in the dark. This is why restoration doesn't look like flipping a switch. It looks like a very slow, very deliberate chain reaction, where every single link has to be verified before the next one is attempted. Rush it, and you don't get partial power back faster. You get the whole thing collapsing again, from a different cause this time. Here's the part that makes restoration genuinely dangerous, not just slow. Eventually, you have multiple islands running independently, and you need to connect them into one grid again. You cannot just close a switch between them. Every island has its own frequency and its own voltage phase, drifting slightly out of sync with every other island, because they're being controlled independently. Connecting two out-of-sync islands is like trying to merge two different rhythms. If the phase mismatch is too large at the moment of connection, you get a violent surge of current as the systems fight to synchronize. That surge can trip protective relays and take both islands back down. Now you're restarting the restoration. So every connection has to be synchronized first, frequency matched, phase matched, voltage matched, before the breaker closes. That takes time and precision, and there is no shortcut. Load is the other half of the fragility. You cannot just reconnect an entire city the moment power is available, because a small island of freshly restored generation can be overwhelmed by demand instantly. Too much load, too soon, and frequency collapses again, right back to where you started. So load comes back in planned stages too. A hospital and water treatment plant before a shopping district, a few neighborhoods at a time, watching frequency the entire way. Every single step, in other words, is reversible in the worst way. That's why full restoration is measured in hours, sometimes days, not minutes. The clearest large-scale example most people actually live through is the August 2003 Northeast blackout. Power started going out across the northeastern U.S. and Ontario around 4:11 in the afternoon on a Thursday. 50 million people lost electricity. New York City wasn't fully restored, every borough back on, until roughly 9:30 that Friday night. Call it 29 hours for one of the largest, most resourced grid operators in the world, executing a plan they'd actually trained for. And that was one of the faster large-scale restorations on record. Some harder-hit areas outside the city took up to 4 days to get fully back. 29 hours to relight one city. That's what it costs to do this correctly, carefully, one cranking path and one synchronized island at a time. Every grid operator in North America is required, by a standard with a name and a number, to have a tested plan for exactly this scenario. Almost none of them have ever had to run it for real, against a total, unplanned collapse. The plans exist. The drills happen every year. But a drill and an actual 4-day restoration across a real, damaged, no-notice failure are not the same test. Cuba is finding out right now what the difference actually is.